Thank you, Olivia, for the introduction. And let me also start by thanking the organizers for setting up this forum for all of us. It's been very helpful. Um, so I'm going to tell you about some work that we've been doing recently in terms of attempting to understand the effect of disorder in the non-equilibrium dynamics of correlated systems. And in general, the importance of understanding disorder doesn't need to be really restated, but very often when we treat correlated systems, we overlook this in part just because of the additional complexity that arises when we include yet this other degree of freedom. However, we know that disorder will have a variety of non-trivial effects. So it's important, to try and understand how the interplay of, interaction and disorder comes into play in non-equilibrium. So in this talk, what I'm going to tell you about is our recent effort to kind of combine DMFT and CPA in a consistent embedding scheme that addresses both the interaction and disorder for the non-equilibrium dynamics of strongly correlated systems. For this talk, I'm particularly going to show you benchmarking results where we calculated equilibrium properties of these models using our non-equilibrium formalism. And then I'm going to show you some non-equilibrium dynamics that we track with this method for an interaction quench in the Anderson-Hubbard model. So in general, the challenge for many body out of equilibrium is the lack of Mann-Low theorem, where we don't have, we cannot relate the state at very long time to the state at the early times by a simple phase factor. And so what that means is that we have to formulate the theory in terms of the Keldysh contour, where we evolve the system forward in time, but also backwards in time towards the initial state again. As a consequence, the Green's function here has to be defined on the Keldysh contour, and it has this texture where the times t and t prime can be on any branch of the contour. On the forward branch, on the backward branch, or on the vertical branch in the case where we have an initially equilibrated thermal state. And the many-body formalism can be stated in terms of the individual Green's functions, lesser, greater, retarded, advanced, or directly in terms of the contour-ordered Green's function from which all the other ones can be extracted. And this is the approach that we're going to use here. Our theory is formulated in terms of the contour-ordered Green's function. The two approaches are equivalent. It's just a matter of convenience sometimes. And also a matter of algorithmic advantages depending on how one goes about solving the problem. So here we're going to be using the contour-ordered Green's function. Now, once you have this non-equilibrium formalism, you can either solve it in the steady state, or you can solve it to understand the transient. If you solve it to understand the transient, you may need to perform this Wigner coordinate transformation where you go from tt prime to an average time and a relative time, where now the average time component plays the role of the effective time of your system. And when you want to understand the frequency domain properties of your system, you'll perform a Fourier transform from t relative to frequency. And that will give you the ability to track the frequency domain properties of your system as a function of time using the average time. You can calculate then key observables in your system. Say you're interested in a field-driven system, you can calculate the current, or you can calculate the kinetic potential and total energy and so on. These are some examples of observables that you can calculate. In general, though, when you have these different Green's functions, the two of them play important roles. The retarded Green's function defines the density of states, while the lesser Green's function defines the distribution functions. Now, we're going to do non-equilibrium DMFT. I don't think I really need to explain DMFT to this audience, but, DMFT initially formulated in equilibrium has since been extended to the non-equilibrium problem and applied with some amount of success to a variety of non-equilibrium problems, including, say, field-driven systems, interaction quenches, or time-resolved spectroscopy calculations. The challenge, of course, is to find a reliable impurity solver, and that remains a challenge, and it's going to come up in in the results that I'll be presenting in a moment. You can use Monte Carlo, you'll have an exacerbated sign problem. You can use exact diagonalization, you'll have the exponential scaling. You can use diagrammatic methods. These will be approximations that will work well in the regimes, in some regimes, but not so much in others. If you're solving the Farikov-Kimball model, we have the advantage there that we have an analytical solution that we know to be exact. And then potentially you can only incur some numerical errors in terms of discretizing your time axis and so on. So the advantage maybe of studying something like the Farikov-Kimball model is that there you have an exact solution and that can allow for you to properly benchmark your solution, let's say. So here what we want to do is look at interaction and disorder. So the model is going to be the Anderson-Hubbard, where we have here our itinerant particle on the lattice. So Jij is going to be a hopping amplitude. And then the second term is going to be a Coulomb interaction every time you have a doubly occupied site. And then you'll have your chemical potential, and then an on-site interaction, that's an on-site energy that's going to be random, V sub I, following some distribution. And that distribution is going to define what type of disorder you have in the system. The non-equilibrium problem will be an interaction quench. So at a given time, T quench, we will change the interaction abruptly from one initial value U sub 1 to another value U sub 2 that we will then keep constant for all subsequent times. So schematically on the Keldysh contour, things will look, like this. The disorder strength is going to be kept the same on both sides of the quench. And you may be wondering what happens if you change the disorder strength across the interaction quench. That's yet another interesting problem that we hope to tackle in the future. But for this talk, at least so far, we've focused on just the interaction quench while keeping the disorder the same, and then asking how does the dynamics of the system change depending on what disorder you have in the system. So schematically, the solution is going to look as follows. We'll start by, guessing some form for the hybridization function. And with that, we're able to calculate the non-interacting range function. From that, then we go into our impurity solver. And we solve that impurity problem for different values of the disorder. And this part of the algorithm in red can be done in parallel, because then you can solve different instances of different disorder configurations in parallel. And once you've done all that, you're able then to do your disorder averaging while solving the Dyson equation for the average, the disorder average range function that allows for you then to obtain a hybridization that captures both the interaction and the disorder. And then we solve the whole thing self-consistently. So depending on what type of disorder you have, you may have to aggressively sample your disorder configuration. This will be one factor in terms of, how much time you spend on the computer solving this problem. In addition to the usual DMFT self-consistency loop. Now, as you can see, this self-consistency loop will readily recover DMFT for the clean system. In other words, if you have only one disorder, if you don't have any disorder at all, this is just your DMFT loop. Now, if you have a disordered non-interacting system, this will just become CPA. All right, so in terms of benchmarking then, we start by solving the Anderson model where we have finite disorder, but the interaction is equal to 0. And so we calculate the densities of states using this non-equilibrium formalism. What we get is something that is consistent with what we would have in non-equilibrium. So in the figure that I'm showing you here, the dashed line is showing you the equilibrium frequency domain solution, while the solid line is showing you the non-equilibrium time domain information that is then Fourier transformed into a frequency domain. Now you'll notice that you have some small negative spectral weights. These are just Gibbs phenomenon that occurs because we have a truncation of the time axis. And besides that, we see a fairly satisfactory agreement between our time domain solution and the frequency domain solution. And one added value of this is that we don't have to do any Fourier transform when we solve the problem through these time domain formalisms. So that's a non-interacting system with disorder, just the Anderson model. And here, these solutions are for, let me emphasize this, these are for box disorder, meaning that we have a uniform disorder distribution between two values. And so the disorder strength here is the two edges, the difference between minus W/2 and plus W/2. That's your disorder strength. And you have, again, uniform distribution between these two edges. Now, if I turn on the interaction, what I get in terms of the density of state is initially, for a weakly interacting system, I see a slight broadening of the spectral weights. But as you increase the interaction strength, you no longer have this broadening of the spectral weight. Instead, you have the formation, the gradual formation of the quasi-particle peak. And eventually, you get the formation of, now, if you push towards where you would have the opening of a gap for a clean system, what you will notice is that as a function of, as I increase the disorder strength, I fill up the gap. In general, the picture is that the disorder is going to shift the critical value of U at which the gap opens up towards a stronger U. And these results are not new from our work. They've been calculated elsewhere, but it's, for benchmarking purposes, quite informative to get these from the time domain solution. Now, that was for box disorder. And when we do CPA for box disorder, we know that we don't see any evidence, say, for Anderson localization and so forth. There's no gap that we see. Consistently, what we see in terms of the disordered non-interacting system is simply a broadening of the bands. So, however, if we look at binary disorder, the picture is quite different. We know, starting from a non-interacting clean system, we have a uniform kind of boring density of state. If we keep the interaction zero, but we increase the disorder strength, we know that we get a gap that forms. We get a disorder gap that forms. On the other side of this, if we keep a clean system, we crank up the interaction, we know that we get a mud gap that opens up. So the question is, what happens when we have a finite binary disorder and interaction? So this is what we're going to be looking at in this figure. So here we're looking at binary disorder. The disorder strength is W. We just have two peaks. So we have equal weight of minus W/2 and plus W/2 in terms of the disorder. So the three panels that I'm showing here show you three different values of the disorder. For the non-interacting system, for binary disorder, you expect here to have the opening of the disorder gap at around W equals 0.7. Okay, so when I start with a weak disorder, what I get is a picture that's consistent with the clean system calculations for the Herbert model, right? As you increase the interaction, you get first formation of the quasi-particle peak and eventually the opening of a mud gap, right? Now, as I increase the disorder strength, what I get for the non-interacting system is that I start forming this disorder gap. I get the suppression of the spectral weight around zero. That's the disorder gap that's forming. But if I start increasing the interaction at this disorder strength, what I see is that I fill up this disorder gap, right? And at the same time, as you increase the value of the interaction, you start to see the formation of these Herbert sidebands. If you push the disorder strength further, now the disorder gap is nearly fully formed, but once again, the interaction fills up the disorder gap. You have the formation of the Herbert sidebands. Now, The one thing I haven't told you so far is that in terms of an impurity solver, we're only using a second-order perturbation theory, meaning that we can go to arbitrarily large U. However, what we can see is that if we push U further beyond the limits that I'm showing you in this graph, those results are not as accurate, so I'm not showing you what they are. However, the trend is kind of expected, and we can explain those trends the same way that we understand the present ones. If I increase U further, eventually, on top of this disorder gap, I start seeing the opening of the Mott gap. So there's quite a rich picture that emerges from combining here binary disorder and interaction, quite different from looking at box disorder and interaction. So then we can ask, how do these interplays come about when we look at the relaxation of the system away from equilibrium? And to track that relaxation, we're going to calculate specific observables in terms of, say, the kinetic energy, the potential energy, and then the total energy. Now, we have an isolated system, meaning that, before we quench the system, it's isolated, so the total energy is constant. And after we quench it, it's still isolated, so the total energy is constant. So we expect that the total energy should go from one constant value to another constant value. Meanwhile, the potential and total and kinetic energy should then be changing in a complementary way across the interaction quench. So then, for box disorder, this is the picture that we get, starting here from weak interaction to moderate interaction, let's say. And then the different curves here are showing you the potential in blue, the total energy in black, the kinetic energy in red, for different values of the disorder strength. The solid line corresponds to the clean system. The dashed line corresponds to disorder 0.5, and the dotted line disorder 0.75. Now, initially, what you see is that as you increase the disorder strength, your kinetic energy essentially is increasing. So that trend continues as you crank up the interaction further, until at some moderate interaction here, what you see is a reversal of this trend. So this is for box disorder distribution. If we look at this same trend for binary disorder, for weak interactions, the trend is the same. As we go towards moderate interaction, we again see this reversal in terms of the long time value of the kinetic energy. It is flipped between the larger disorder and the weaker disorder. This, if we look at the spectral, the density of state, we notice that effectively this is happening where we have a depletion of the spectral weight around the Fermi energy. As we've just mentioned, looking at the density of state, you can then expect that if you push the disorder strength further, something else will happen, and that is what we're seeing on this right-hand side plot here. So this is just a continuation of the data of the left-hand side, right? So now, if you push the disorder further, this trend is shifted. Now you no longer have something that's so dramatic. It's just this pattern of kinetic energy lines. So taking things further, we want to understand how this system is thermalizing. In other words, if we start the system off in equilibrium at some temperature, what is going to be the long time temperature of the system after it has settled into its steady state? And to do that, we identify a thermalization time where we say neither the potential nor the kinetic energy are no longer changing in any significant way. And at this time, we can calculate the retarded and the lesser Green's function. From those, we can perform a Fourier transform, and then we can apply the fluctuation dissipation theorem to extract a distribution function. When we extract that distribution function, in case we have not yet achieved thermalization, what we observe is that that distribution function is changing quite widely. However, once the system is thermalized, we see that the distribution is no longer changing in any significant way. And with this distribution function, then we can pull up a temperature by simply fitting a Fermi-Dirac distribution function around the Fermi energy and extracting then what the temperature is. When we do all that, we obtain the following picture of the final temperature of the system as a function of final interaction for different disorder strengths. So we quench from U equals 0 to this final U, and at this final U, we then have different disorder strength. What you see is on either side of this gray thick line, a reversal of the trend. On the left-hand side of this gray line, what you have is that higher disorder corresponds to higher temperature in your final state, whereas on the right-hand side, higher disorder corresponds to higher temperature. I will note that this is also happening in a relatively weak interaction regime. So we are essentially observing some type of a crossover between a region where the dynamics of the system is dominated by disorder into a region where the dynamics of the system is now more impacted by the interaction. And this understanding this in further detail and kind of quantifying precisely what is happening is something that we are now working on. And some of the ideas that we're exploring for this came up actually when I was visiting the CCQ last time. So we are, doing some calculations, and they're rather promising, but they're not final yet. So I'm not showing you those results just yet. But I think we're kind of understanding with more confidence what's happening in this disorder to interaction dominant regime crossover. Now, the next kind of sets of results that I want to present to you have to do with understanding a little bit further how the disorder is going to affect the relaxation in this discontinuity at the Fermi surface. This is kind of picking up from something that Martin and collaborators did some years ago, where they showed that if you do this, when you perform this interaction quench in a clean system, you get this discontinuity at the Fermi surface, the magnitude and the relaxation of which is dependent on what the final interaction in your system is. So here then we ask, how does this change if we have disorder? It turns out that it changes in a relatively non-trivial way. And so in this figure here, I'm showing you what this discontinuity, the dynamics of discontinuity here at the Fermi surface for a clean system versus for a disordered system. Here, the label for disorder is going to change from W to omega, simply because this calculation is done for Gaussian disorder. I can tell you about the details, but it's not particularly important, let's say. And so we want to understand further exactly what's happening here. So here I'm going to show you the magnitude of this discontinuity for a clean system as a function of the interaction. What you see is that initially, at weak interaction, you have this plateau that arises, the plateau at very high delta N. If you keep cranking up the interaction, eventually you start having these oscillatory behavior. And in between, you have a regime where the system thermalizes fairly quickly. So what happens when I do the same thing, but for a disordered system, I get a suppression of this plateau. I get a suppression of this plateau and a suppression also of the oscillations in a regime where I have delta N that's performing this collapse and revival. So this is a similar picture, except now I'm showing you at constant U for different disorder strengths. And again, the picture is consistent as a function of the disorder strength. What you will see is that if I have no disorder, the plateau is high up here. If I turn up the disorder, the plateau is suppressed, so I have fast thermalization. If I go to stronger interaction, what you see is that for clean system, I have high amplitude in these oscillations. If I crank up the disorder, I get suppression of these oscillations. If I push the disorder further, eventually I get fast thermalization. So then what you need to do is scan a space of interaction and disorder and see precisely what happens. Previously, this was done in terms of, so the left-hand plot is what was done by Martin and collaborators. But now we're doing this as a function of the disorder strength. And this allows then for us to have this type of phase diagram on the right-hand side, where we have a region where we have a saturation, where this plateau is finite. And then the region in green is this region of fast thermalization. And on the right-hand side, we have the region where we have these oscillations. Note that on these plots, on the right-hand side, you have the magnitude of this delta n, where you have this plateau. On the right-hand side, you have the amplitude of the first oscillation. The bottom line is that you can see very important enhancement of the thermalization of the system when you put on more disorder. So let me just sum up the message of this talk. We have implemented an embedding scheme that combines both DMFT and CPA away from equilibrium in order to address the interplay of interaction and disorder. We've done some benchmarking to understand the equilibrium densities of state, both for box disorder and for binary disorder. This density of state is consistent, say, with the Anderson model, where we have no interaction, with the Hubbard model, where we have a clean system. In the Anderson-Hubbard model, you see an insulator to metal transition that's driven by disorder. And then when we perform an interaction quench in the Anderson-Hubbard model, we see nontrivial dynamics as a function of the disorder strength. When we perform the thermalization analysis, we see that disorder can tune the final temperature of the system and does so in a non-trivial way, depending on how strong the interaction is in the system. Finally, we see different regions in parameter space of fast thermalization versus oscillatory relaxation, depending on both the interaction and the disorder. To wrap up, let me just acknowledge briefly my collaborators. We have two new additions to the group at the University of Buffalo. Ali Abou and Shangji Liu are the students working with me in terms of doing further calculations, including for the things that I mentioned, ongoing work for binary disorder, and then for understanding this crossover between disorder-dominated relaxation and interaction-dominated relaxation. Kunal is a student who's working with myself and my colleague John Han at the University of Buffalo in trying to understand the emergence of variable range hopping from the quantum Hamiltonian when you have, disorder. And then, yes, thank you for your attention, and I'm happy to entertain questions.
Thank you very much, Herbert. First question, we have Antoine.
Thank you, Herbert. I'm wondering whether you could comment on what you think are the limitations and strength of the CPA approximation to treat the disorder.
Yes, that's a very important point. So let me go back to the slide on the densities of state. So, when you do CPA for box disorder, what you see is this broadening of the densities of states and nothing else that happens, right? And CPA in general is not going to show you anything that resembles Anderson localization. If you put a field on the system, and this is, shown in the work that I'm now doing with my colleague John Han, you do not see, even for a system, the type of Lifshitz tails that you expect to see in these systems. And so those Lifshitz are going to be important to understand the emergence of localized states. CPA is not going to capture that. However, what it does fairly well is to capture the overall broadening of the density of states. The value, of course, in doing binary disorder is that you get non-trivial densities of states that you can capture readily with CPA. And so then, doing binary disorder with interaction allows you to see some, less trivial effects of disorder than you would for box disorder.
Perhaps, as an add-on to my question, do you think that there are interesting effects associated with the dynamics that could be explored on the vicinity of the Anderson insulator to metal transition? So obviously that would necessitate using the scheme going beyond CPA.
Yes, and that's a question that we are right now looking into, trying to understand, can we see emergence of localization by kind of enriching the scheme somewhat.
Because of course you can do DMFT, you can do inhomogeneous DMFT on a big finite size system, and that would have Anderson localization properly.
Yes, that's a question that came up in discussions with Andy at the CCQ. It's something that one of my students is going to be looking into. Yes.
Okay. Thank you.
Thank you.
Well,
hello.
Yes.
Do you hear me?
Yes.
Here is Henri Aloul. I think you are missing all the peculiar effects which are connected with the specific disorder of correlated systems. Well, we know very well that in correlated electron systems, the disorder can be very strong and give you localized states, which you totally miss. Even if you put a single substitution in the copper oxygen plane, you get a localized state in which you have strong magnetic effect which appear. So I am a little bit scary about the idea that CPA will well, I think it's not a very good representation of what happens in the specific very correlated electron systems.
That's a very good point, and it's so we refrain from pushing the disorder strength very far, as you can see in the solutions that I'm presenting, in part because we know that the physics will be very different from what we can capture with CPA. However, for weak disorder, I think it is fair to assume that we can capture some reasonably well what's happening in the system.
I think this is probably the case if you do substitutions in the rock salt layers far from the copper oxygen plane, and that probably will describe this kind of situation. But this is not the usual disorder which happens in the real materials, I think, because you have enough disorder very near the copper oxygen plane, which drives many effects connected with the correlations.
The point is well taken, and I think it only emphasizes the importance of, us trying to tackle this problem from one end, right?
I agree.
Yes, it's again the point is very well taken.
Well,
yes. So I would follow up on Antoine and the general question is CPA. So my naive question is, what's keeping you from using the typical medium theory of Christoph, who's in the audience? And could you also comment on the alternative approach that you are taking in the results you were showing us on the distribution function? Because that's not CPA as far as I understand.
So, so two parts to your question. First part, why we're not doing typical medium. We're thinking about it, but so far I should admit that I'm somewhat hesitant, but we're thinking about it. The thing with a typical medium is that you have to do an averaging. You change the way that you do the averaging, and you do the averaging essentially on the densities of states, right? However, in a non-equilibrium formulation, you do not necessarily have a well-defined density of state. So that object on which you're doing this averaging, doesn't have the physical properties that you would argue for the equilibrium problem. So this is, not to say that we may not be able to implement some variation of typical medium, but just to explain why, we're a little bit timid about, going for it. And in terms of the last set of results, essentially what we're doing here is we're writing a formalism where we can integrate the disorder out. And that's why we're doing Gaussian disorder in the solution, because it's a form of disorder that we can integrate. And once you've integrated that exactly, you get some perturbation theory in terms of the disorder strength and the interaction. So that's what's happening here. And so this solution is again going to be limited to relatively weak disorder, just because we can only solve that perturbatively.
All right, thank you.
Thank you. And certainly for your first question, I hope that I answered your question satisfactorily, because yes, it's an important point, right? Why don't we just do this? But, yeah.
Any other question? Nothing. There are other questions.
Maybe
so
I'll just say a couple of words. I think André-Marie
has a question.
Oh, no, just very simple. Is there any regime where you can, quantify the relaxation as exponential or power law or anything like that? Or that didn't seem to be any simple expression, right?
So my student is right now calculating the relaxation time for these two different models. We haven't yet done any type of back of the envelope, if you would, calculations to see what we can fit on the results that we have. Hopefully I will have something to say about that in the near future, but we don't have. But there are trends, but the results are preliminary, so I hesitate to speak on them at the moment. But yeah, it's an important question indeed. Yeah.
Thank you. Thank you.
So I just wanted to conclude the session. Well, first of all, let's thank Herbert once more, as well as Utah, who stayed up late. And I wanted to conclude the session by wishing everybody a happy holiday season, but also encouraging everybody to encourage members of their group to actually participate and attend into the symposium. We are still having a reasonably large audience, but not as large as the beginning. So it would be nice to start 2025 going back up to 80 or 90 participants. That would be wonderful. And also, please don't hesitate to send to the organizers suggestions for possible topics and speakers. This being said, we'll see you at the next symposium, which is on January 13th.